I can go over those last few on page 4. These are the ones you want to go over, right?
Yeah.
Okay.
Or confusing, because then I'll end it up as y equals 1.
Yeah. Yeah. It's not always the case, but that's the a lot of the problems that end up looking like that.
Spreadsheets. Picture.
Yeah.
Maybe at the end of February. I see you.
Okay, so we know that this is an issue for us. If we have 0 raised to the 0, it doesn't quite fit into that L'Hopital's rule that we want. We want that 0 over 0. So you know that all these situations you're going to do log differentiation. So we're just going to focus our attention on just that function. Let's call that function x to the x squared. I have to sit in the very back there, but you have your book back. Okay. You're trying to finish that.
Yes.
Okay, yours is right there.
Really?
Yeah.
Thank you.
So if we want to work with a function that's in the form of x to the x squared, this is a variable raised to a variable. We don't have an easy way to work with this unless we can get this to a different form. So we're going to use log differentiation. So now that the x squared is inside, now that this function is inside a log expression, we can cause that exponent to come down, part of log expansion, right? Now, this is still not quite in the form of what we want. It's a limit problem. We know we're trying to head towards L'Hopital's rule, but if we want to do L'Hopital's rule, we need this to be numerator over denominator because I need something to show me either 0 over 0 or infinity over infinity for me to do L'Hopital's rule. Go with that, Max?
Yeah.
Okay, so if we want that to happen, we have to force this to show us numerator and denominator, but right now it's not quite showing us, right? Everything's in the numerator. So I want to force that x squared in the denominator without changing the overall value of my expression. So I'm going to make it natural log of x divided by 1 over x squared. Okay, any questions with that? Now, these are the same things. You know, this is not the way that we would normally write something. We're just, you know, so there's two things that's happening, right? We're trying to maintain the same value of this, but we're also trying to get into this form. So that's why we're forcing it into something that looks strange like that. Okay. So now let's see what happens. Limit as x approaches 0 from the right side of 0, natural log of x. So here's my numerator, here's my denominator. I'm going to test 0 here just to see if I can get it to look like one of these forms. If I plug 0 in, remember, if you see a one-sided limit, you always want to try plugging in the integer value. Don't do decimals yet. So if I plug natural log of 0, that's undefined, right? Natural log of 0 is undefined. So because it's undefined, let's now look at the one-sided limit. If we're approaching 0 from the right side of 0 for natural log of x, if you think about what natural log of x looks like, right? If I'm approaching 0 from the right side of 0, the y value is getting closer towards negative infinity. So my numerator is headed towards negative infinity. My denominator, if I plug 0 in for the x, 1 over 0 is undefined. That doesn't work, right? But what if we did, now that we got the 0 to show it doesn't work, now we can look at decimal values. So let's do 0.1, then 0.01, then 0.001. The denominator is getting smaller, which is causing this overall fraction to do what? Get larger towards positive infinity. And we just want to prove that this is happening so that we can do L'Hopital's rule, right? This is not the answer, but at least we now have the conditions where we can now apply L'Hopital's rule. L'Hopital rule says find the derivative of the numerator, find the derivative of the denominator, reevaluate, and we're now, after that, we should be able to hope for something that is more than just an undefined form. We should be able to now get to a real number. So derivative of natural log of x is 1 over x. X, 1 over x squared, this is really x to the negative 2. I mean, we can go through quotient rule, but I think it's easier to just rewrite it and go through the power rule instead. So the derivative of x to the negative 2 is negative 2x to the negative 3. Okay. I do want to evaluate 0, but let me clean this up a bit. I think it's easier if we evaluate after we clean this up. So this is 1 over x divided by negative 2 over x cubed, which is the same thing as 1 over x times negative x cubed. Right, dividing by a fraction is the same thing as multiplying the top by the reciprocal. So we get negative x squared over 2. So now we should have a different version of our problem for us to evaluate. So we always evaluate the real number first, no decimals. So if I plug 0 in, I'd get a real number, right? 0 over 2 is 0. So this is good. We're now moving closer towards our answer. So we know we've proven that the limit of this function, x squared natural log of x, is equal to 0. But it's not truly our full limit, right? Because we manipulated this equation to get into that form. So ultimately, the 0 is for the x squared natural log of x. We're still trying to solve for y, right? Our y is really what we're after. So then we can say natural log of y is equal to 0. Basically saying natural log of what value is equal to 0. If I raise both sides with e as the base, I get y equals e to the 0, y equals 1.
Mm-hmm. The question in the 6.12 note.
Mm-hmm.
It was number 5 and number 8. And also number 6.
What pages are they? Okay, page 12. Okay, which problem? Mm-hmm. The thing to know about arctangent is how the graph looks. So the graph looks something like this. So it's kind of like the tangent graph, but it's kind of flipped sideways. And so rather than 2 vertical asymptotes at negative pi over 2 and pi over 2, it has 2 horizontal asymptotes at negative pi over 2 and pi over 2. And the graph looks something like this. We just have to kind of look at the graph, see what happens. If we're approaching negative infinity, our tangent is flattening out towards negative pi over 2. As we're headed towards positive infinity, our tangent is headed towards a y value of pi over 2. Yeah, we have a special rule for this, which we'll talk about more in our series unit. So yeah, let's not worry about this for now. We'll have a more efficient way of getting to that answer. But yeah. Okay, so I can go over any questions that you guys have from the packet, from the quiz review packet. So Max was asking about L'Hopital's rule off of worksheet 1. So I did one example of that. I can go over worksheet 3. I can just you guys, so you guys can kind of let me know what you want to do.
Whether to use tab method or not. Like, how do you know which one to use?
Yeah. So I would say if you see natural log in the problem, then don't do the tab method. It's not going to work. If you don't see natural log, so if you see like exponential paired with algebraic or algebraic paired with trig, those are your good candidates for tab. Yeah. So if you see natural log, you're kind of forced into this original formula. And if you see natural log in the problem, then just make sure that your f is always your log, and then the other term is going to be your g prime. Okay, which page? Okay.
First one was number 3. Like I get why it approaches 0 because of the x to the 3 halves, but what would sine of 1 over x approach? Like, do we need to like worry about that, or do you just ignore that when we're like looking at the equations?
Yeah, sine of 1 over x is kind of strange. It kind of oscillates, but it just oscillates between -1 and 1. So technically this limit doesn't exist, but that x to the 3 halves is overpowering whatever little oscillation that's happening. So this is approaching infinity. This is going to take control over this entire denominator. So even though that's a slightly oscillating value between -1 and 1 is going to be, it's not going to matter if this is like in the billions, right? It's going to head towards 0.
Like, what does like the 1 over 0.001?
So once I got to this step, I'm always trying to plug in that number that I see, right? If I see one side limit, I'm always considering what's happening here. At pi over 2, cosine of pi over 2 is 0. We know that cosine of 0 doesn't exist, right? So if we're approaching pi over 2 from the left side of pi over 2, that means we're headed towards pi over 2. And we know that if cosine is 0 at pi over 2. If we get closer and closer towards pi over 2, that cosine value is like a really, really small number, right? It'll get closer and closer towards 0, which means I just use an example like 0.000001. This number is getting smaller. If my denominator is getting smaller. Shouldn't that get larger? Right. Let's see.
So wouldn't the one be negative? It's -7.
Yeah, I think I made a mistake there. That denominator getting smaller and smaller should force this to be negative infinity. Okay. Which period?
What third period?
You can take it then.
Okay, thank you so much. I realize.
Okay.
Last one was number 8.
Mm-hmm.
I'm just confused about why, 2 would be infinite in determinant. So does infinity not count as indeterminate or?
Hmm. Oh, I need to finish it. My brother calculated. So, yeah. Give me a scratch sheet. Sure. Oh, yeah, just use it there.
Mysterious. On the quiz, will there be like the further logistic functions stuff, or you're gonna have to do the L over 1 plus C to get a negative K?
No.
It's just the form that we learned this.
Yeah, this one, I don't know why. Maybe it's because it's at 0. We're looking for 0 over 0. That's why, yeah. But technically, it is indeterminate form. We are getting infinity over infinity. Yeah, sorry, it's a bad question.
Do we always start with like a positive sign or is it?
Yeah, always start at the positive. Upper left corner is positive, and then positive, negative, positive, negative.
So the first.
Stays negative, right? Yeah. Use the calculator too if you want, Frankie.
When you're doing like time method and you have like cosine to 5x, it when you're taking the integral of it,
Yeah.
Is there always like a pattern for the coefficient?
Yeah. It's because of u substitution. If you go to u substitution, it'll produce 1/5. And so each time you do u substitution, the u is going to be 5x. It's going to produce another 1/5, and it's going to keep just tagging on to the previous 1/5.
Do you want us to show the?
You don't have to. No, you don't have to. But I want to show you u substitution so that you understand where it's coming from. Yeah, but you don't have to show it to me on the quiz.
Do you have like a general like checklist or anything that we should have up to speed for the quiz tomorrow? Like, from, like, the general topic is. There's like a couple extra things that happened in the packets, like the form that of like the logistic equations that you said was gonna be there.
Yeah, I mean, the logistic equations will just look like what you see in the quiz review. So I think quiz review is going to be a really good. Oh, no. Yeah, if you can get through worksheets 1 through 3 and you feel like you can take blank versions of them and get a really good grade, you should feel good about quiz.
I forgot this, but when we're doing the area and volume ones, when do we square like I know like we take like the difference between the top and the bottom, but when do we square it and when do we like when everything's like
Let me
this
see.
area and volume? It's not like this, but like whenever we have like two curves and we're finding it's like the area or the volume it's like the volume, when do we square it?
We only square it if it's like volume, if it's like this method, washer method,
Okay.
cross section, which we're not going to see on the
Okay.
yeah, it's just integral.
Did you just go over like number 6 on the quiz review for worksheet 2?
Mm-hmm. So by looking at this problem, we know that there is an issue at 5, right? We know that 5 is causing that denominator to be 0. We can't do a definite integral usually if one of the boundary doesn't exist. But we know there's an issue at 5. There's at least continuity at 5. So we know this is one of those improper integrals, definite integrals that we can set up. We know that there's an issue at 5. So we'll put a B there and we'll approach 5 from the left side of 5 because we know that we're looking at that region between 0 and 5. We can get as close as possible to 5, but we can never reach it. So that's why 5, approaching 5 from the left side of 5. So once I have this set up, then I'm just going to approach this problem like I normally would with a definite interval problem. I'm going to go through, in this case, use substitution, trying to find a rule that I can use with my definite interval. So my u is 5 minus x, my derivative is -1, dx equals du times -1. So I'm just making my substitutions there, replacing this with u, replacing dx with -1 du. But the 5 minus x is out of place, that u is out of place, so I'm forcing it to the numerator, making it u to -1. So everything looks pretty good here. This is a nice power rule problem for me. I can now do power rule, negative u to the 1/2 over 1/2. I'm just adding 1 to the exponent, which cleans up to be -2u to the 1/2. Replace the u back in terms of x. Now that I have my antiderivative, I'm ready to evaluate my bounds. And upper bound first, minus lower bound. Now, whenever I evaluate my bounds, I'm always going to test my real number first, okay? Because if this works out, then that's great. If it doesn't work out, then I can play with decimals. Okay, so let's plug in 5 first. 5 minus 5 is 0. That's fine. And then when I plugged in 0 here, that gave me a real number as well. So 0 plus 2 plus 5, that's a real number. If it's a real number, this converges. This tells us that even though we're approaching an asymptote, we can still find a definite area. So this proves that we're getting a real number out of our process. If either one of these is infinity, then we can say divergence or infinity, and the definite interval doesn't exist.
So the only 2 solutions would be converted.
The real, no, that's right. Convergence to a real number, divergence to positive or negative.
Could you go over number 5? I understand the like splitting with the A plus B and stuff like that. But once you get to limit as t approaches infinity, 3 natural log,
Right.
that, yeah.
So we're gonna just kind of forget about this natural log. We're just gonna focus on this statement. And then by plugging the upper and lower bound here, it's really b minus 1 over b. And we know that if we're approaching infinity and we have a numerator and denominator, we're looking to compare degrees. If we compare degrees, degrees are the same, then we just take the ratio of the coefficients, which is just equal to 1. Because that's 1, we know, okay, this is essentially asking what is 3 natural log of 1 if we have 0. So we're able to remove that.
What does it mean when you said no impact when, you had 235?
Oh, right. 0 and 1 have no impact because this graph only starts at 2, from 2 to infinity. So 0 and 1 is not, the asymptote is not impacting my definite interval. If it did, then I would have to worry about splitting up or dealing with approaching 0 from the left or 1 from the right.
Did you work through that one?
Number 5?
Yeah.
Okay. So we're going from 2 to infinity. We know that this is a improper depth integral, but the rule for this is not an easy use substitution because there's no u value that can work, right? Power rule doesn't work. So this fits into a partial fraction decomposition because my denominator is factorable, or my denominator can be split up into different factors, and my denominator has a higher degree than my numerator. So I know that my integral process is going through a partial fraction. So the way I use partial fraction is 3 over x times x minus 1 equals, we want to split this expression into a over x plus b over x minus 1. And I do the cover-up method, which says, let's find the factors for both my denominators. So this is x equals 0, that's x equals 1. If I want to resolve this a, I'm going to cover up the x and then plug 0 into the remaining expression of my problem. So 0 in for x, 3 over 0 minus 1 is 3 over negative 1, which is negative 3, so a is negative 3. For x minus 1, my factor is 1, so I'm going to cover up x minus 1, plug 1 into the remaining expression, numerator and denominator. 3 over 1 is 3, so that's my b value. So now I have an integral problem that's a little bit easier to resolve because now these are two separate, easier problems. Negative 3 over x and 3 over x minus 1.
So is a negative the only thing that's new?
Yeah, that's where I messed up. And so that threw everything off.
Okay, so if I got the old answer, even with the negative, like I got negative, but.
Yeah, this, the reason why this plus wouldn't work was because we're not able to stack them and convince ourselves this ends up being infinity plus infinity, which diverges.
Yeah.
But if it's negative, we're able to manipulate it in a way where we can use log properties to force that numerator and denominator to give us potentially a real number.
Okay.
On the packet, like the original packet of all the stuff from AB, like FRP, on page 13, I don't understand what
Page 13 of the quiz review.
no, it's the original packet.
Oh, okay. This one?
Yes.
Okay, which
For
problem?
number 11.
A11. Yeah, this. I feel like I'm going to cover this a little bit more in more detail when we talk about P series in our series units. So let's not, yeah, I'm not going to test over that since we'll do a better job covering that in our future unit.
Could you tell us like for so like everything that's gonna be on the quiz, like how to identify like each type of problem? Like,
Oh, you mean like this falls under what category?
yeah, like if it's a random like problem. Like,
Mm-mm. Yeah, you're gonna have to, I mean, you're gonna know it's gonna be one of these categories, so it's not gonna veer far off this. So you know that you're gonna pretty much see, you'll see one or two integration by parts, you'll see at least one improper integral, you'll see a partial fraction, you'll see Euler's method, you'll see legitimacy equation, you'll see arc length curve, you'll see L'Hopital's. So
how many questions is this gonna be?
like 8 or 9. It's like 3 pages. So it'll be shorter than, slightly shorter than these worksheets.
Go back to that 5.
Mhm. This one here.
The other 5, the one we were just talking about. So that's the very end.
Oh,
You got 1. Where's the 1/2 from plugging in 2?
that's right. Plug in 2.
So the B just, plug it in because you already got 1.
Okay, so I think I skipped some steps here. Let me do this one.
So you compare degrees.
Compare degrees with this, which gives me 3 natural log of 1, which is 0. This becomes 3 natural log of 1/2. This is fine. Negative 3 natural log of 1/2. But we could go a little further and make it 3 natural log of 2 to the negative 1 and bring that down as 3 natural log of 2. I just want to show this to you because if this multiple choice on the AP exam, they'll probably more likely show it in this form rather than this. That's what this.
Okay.
But street response, this is fine.
Could you go over like what each I think for like LIATE, what like each one of those means?
Yeah. So L is for logs, I is for inverse trig, which you're not going to see. A is for algebraic, T is for trig, and E is for exponential.
On page 14, the steps on the very bottom.
Page 14 of the review packet.
Yeah. The Euler method. Why can't you just like plug in the X? I get why we're doing it, but I feel like that's just. I'll plug in 2 and 3. I guess it wouldn't work, but why shouldn't I?
So the idea with Euler method is that we're making approximations using linear methods. So it's at best going to be just an approximation. I mean, our answer is always an approximation. So we're just gathering. But you're right. I mean, if we want to find the exact value, we can just plug 3 in and get a much better.
So can I check my answer with that, or would it be kind of off?
It's gonna be different because this is gonna be an approximation versus an exact value.
The more step, or the more like time you do it, the closer your approximation will be.
That's right. Okay. But for these problems, you're never gonna have to worry about how accurate your approximation. You just have to do the approximation they're asking for, and then that's that. Yeah. But yes, yeah, the more steps we take, the more input we receive, and the more accurate our information is going to be, our approximation is going to be.
Or logistics, is it basically just like what type of problem are they gonna like ask them? What is it gonna be like more like question 7 or like? On week 1.
Yeah, I would go through all the logistic problems in between worksheets 1 and 3, and 1, 2, and 3, and you're just playing with one of those two types. And so it may be asking you to rearrange it, trying to find a limiting value. It may ask you to find the K value. So, but ultimately it's just playing with those two equations, those differential equations, and identifying the different pieces of it. But you're not gonna be asked to solve that differential equation. A lot of times just using those forms to pick out the different pieces of information. So yeah, see if you can go through all those types and
And do you know where on the review there's arc line?
yeah, arc length. Uh, 13 and 14 on page 5. Page 10 and 11, 12 and 13.
Fairly simple, right?
It really is, yeah. You're just using the formula. Yeah. I think amongst all these topics, the arc length should feel the easiest. It's just the most straightforward.
You go over like on page 17, you go over like 15.
I see it. This one here?
Yeah.
So we know that this is a limit problem, which you're expecting this to be some sort of L'Hopital's problem. But L'Hopital's rule is not going to work unless we get a numerator denominator to show us to get into that form. So this is variable raised to variable. We're going to use log differentiation to allow for these two to be arranged a little bit easier. So I'm going to take the natural log of both sides, bring that tangent down, and now I have this. But this is not quite ready for L'Hopital's because I want to be able to get something numerator denominator. I'm going to force that tangent to the denominator, which is same thing as cotangent in the denominator. Right. I can't just put the tangent below because then I'm changing the value. If I put cotangent below here, cotangent is the same thing as tangent in the right.
Oh yeah, because I'm 1/10.
Right. It's 1/tangent. So now I'm in the form that is more suitable for potentially L'Hopital's rule. So I'm going to plug in pi over 2 to see what's happening here. The natural log of 1 is 0, so that works. Cotangent of pi over 2 We know that cotangent is the reciprocal of tangent. Okay. Cotangent of pi over 2 is yeah, it's undefined, but if we're approaching pi over 2 from the left, it's getting smaller and smaller. So this is approaching 0, this is approaching 0, so they're both suitable for. So then we find the derivative, u prime over u, or natural log, okay, see in class. Cotangent becomes negative cosecant squared x. If I clean this up, just going through a series of cleanup so that I just have an easier time with my evaluation. I get it all the way down to negative cosine times sine. And now if I plug pi over 2 in, cosine of pi over 2 is 0, sine of pi over 2 is 1, 0 times 1 is 0. So we know the results of my expression is 0. And now I can go back to my problem here. Natural log of y is equal to 1 or 0. And then therefore y must be equal to 1.
All right. All right, thank you. And is the homework and like are you gonna be checking like the quiz review worksheet 3 like tomorrow or
Yeah, I'll check worksheets 1 and 2 probably like Monday,
Monday?
along with 9.1 and 9.2 homework. Yeah, so I'll do that all after the quiz. All right.
And is it gonna also include 9.3 homework on